Welcome back, everyone, for another deep dive. This time, we're getting really, really small
Small or small.
to the world of leptons and, their role in quantum tech, believe it or not.
It's pretty wild stuff. I mean, these tiny particles.
Yeah,
Yeah, they're having a big impact.
huge impact. So we're going to try to unpack that today using an article by Jürgen Schneppat called, and get ready for this title, Leptonen, Baustein der Materie in der Quantentechnologie.
Catchy, right.
Really rolls off the tongue. But before we get too deep into that, let's sort of set the stage. When we say leptons, what are we even talking about?
Right, good place to start. So leptons, they're these fundamental particles, meaning you can't break them down into anything smaller. They're like the building blocks of matter. And what makes them special, what makes them leptons, is that they don't interact with something called the strong force.
The strong force.
Yeah, one of the four fundamental forces of physics is what holds the nucleus of an atom together. But leptons, they're like, nah, not interested.
So they're kind of like the rebels of the particle world.
Exactly, doing their own thing. And Schneppat even calls them an exclusive club of particles.
Nice. So who are the VIPs in this exclusive club?
Well, the most famous one you've definitely heard of, the electron. Tiny negative charge, hangs out in atoms. That's our superstar. But then we've got the muon.
Yeah.
Much heavier than the electron. And it's unstable. Like, it doesn't stick around for long. Kind of a mystery to scientists.
Ooh, intrigue.
And then if the muon is mysterious, the tau particle is like a full-blown enigma. Even heavier, even more fleeting.
It sounds like trying to study those would be a nightmare.
Yeah.
But wait, there are more, right? We can't forget the neutrinos.
Ah, yes, the ghosts of the particle world. Schneppat actually uses the word ghostly, which I think is very fitting. These things, they're so light, they barely interact with anything. They can pass through like light years of lead without even noticing.
That's insane. So how do we even know they exist?
It takes some seriously incredible detectors to catch them.
I bet. Okay, so we've got our electron, the muon, the tau, and these ghostly neutrinos. Schneppat also talks about this lepton number thing. What's that all about?
Right, so the Lepton number is this kind of like cosmic accounting system. It's this fundamental law in physics that says the total number of leptons in any interaction, it has to stay the same. Each type of lepton has its own number and they have to balance out.
So it's like a rule that keeps these particles from just appearing and disappearing willy-nilly.
Exactly. There's a balance. And it actually has implications for how we understand and use these particles in quantum technology.
Okay, see, now we're getting into the good stuff. So how are these leptons actually being used in quantum tech? Like, what are the practical applications here?
Well, in a lot of quantum computers, electrons are the stars of the show. They can act as these things called qubits.
Qubits?
Yeah, it's like the quantum version of a bit. And the way it works is electrons have this property called spin, and we can control that spin using electric and magnetic fields, and we can use that to represent information, like a 0 or a 1.
Wow, so it's like using the spin of an electron to store information. That's mind-blowing.
It is. And what's great about electrons is they're relatively stable, which is really important when you're trying to build a reliable quantum computer.
Makes sense. What about those other leptons, though? The muons, tessis. Do they have any use in quantum tech?
Well, they're not used directly as qubits, not yet at least, but they're really important for research. Like, muons are used in particle accelerators to study, the fundamental forces of nature. And the more we understand about these particles, the more it informs our work in quantum technology. That all kind of feeds back into each other.
So even if they're not on the front lines of quantum computing, understanding them can still lead to breakthroughs.
Absolutely.
Now, what about those neutrinos? They seem pretty impossible to work with, given that they can pass through, well, everything. Any practical use for them?
You'd be surprised. This is where things get really interesting. Because they can pass through anything, they're actually theoretically perfect for communication. Like, imagine sending data through the Earth itself. No cables, no satellites, nothing to intercept the signal.
Wait, hold on. Transmitting data through solid rock? How is that even possible?
That's the challenge, right? And that's why scientists are working on developing these incredibly sensitive detectors, trying to figure out how to reliably create and detect these neutrinos.
Sounds like something straight out of Star Trek.
Yeah.
But if we could crack that, the possibilities are pretty mind-blowing.
It's a huge undertaking, a huge challenge. But the payoff could be enormous. We could be talking about a communication revolution. So we left off talking about neutrinos and communication.
Yeah, it's a pretty wild idea. Using neutrinos to send messages.
It is wild. But, it's not as far-fetched as it sounds. Schneepat, he really lays out the case for it. I mean, think about it. Trillions of neutrinos are passing through us right now.
Through us.
Yeah, right through us.
Yeah.
Every second. And we don't even feel a thing.
I guess that's why they call them ghostly.
Right, it's because they barely interact with matter at all, which on the one hand makes them ideal for communication because nothing can block them. But on the other hand,
It makes them really hard to detect.
exactly, it took scientists decades, to figure out how to even prove they existed. And even now, to study them, you need these massive underground detectors, like huge.
Underground. Why underground?
You got to shield them from all the other stuff flying around out there. Cosmic rays, other particles, all that noise. So they build these detectors. Sometimes they're under mountains. Sometimes they're in, like, abandoned mines.
Crazy. So what makes it worth all that trouble?
Yeah.
What's so special about neutrinos that we'd go to all that effort?
It all boils down to that one unique property. They can pass through anything. Imagine sending a message, and it doesn't matter if there's a mountain in the way, or an ocean, or even a whole planet.
Okay, now I see why Schneepat's so excited about this.
It's the ultimate secure communication channel. Because nothing can block it. Nothing can intercept it.
No more hackers. Sign me up for that.
Right, and that's exactly why so much research is being poured into this, trying to figure out how to create and detect neutrinos reliably so we can actually build a communication system around them.
That's amazing. So while we're waiting for neutrino-powered internet, what about the other leptons? We talked about muons and tapas, how studying them can help us understand quantum tech, but what are they actually being used for right now?
So muons, for example, they're used in this really cool technique called muon spin spectroscopy. It's kind of like using these tiny magnets, atomic scale magnets, to probe the structure of materials.
So instead of using a giant microscope, we're using muons.
Yeah. They can tell us all sorts of things about a material, like how the atoms are arranged, if there are any defects, even what the magnetic fields inside are like.
And this helps us with quantum tech, how?
Well, it helps us understand materials at a really fundamental level, which is important for building all sorts of new technologies, including quantum computers. Plus, there are other applications too. Schneepat even mentions how they've used muons to study the pyramids in Egypt.
No way. They use muons to look inside the pyramids.
Yep. To see if there were any hidden chambers or passageways.
That's incredible. So we're using subatomic particles to uncover ancient secrets.
Exactly. It just goes to show you the study of these particles, it leads us in all sorts of unexpected directions.
That's all connected.
Oh,
Okay, but let's get back to those muon anomalies we talked about earlier. The fact that they seem to have stronger magnetism than our current theories predict. Any updates on that?
That's still a big mystery. It's one of the most exciting things happening in physics right now, because it suggests that maybe, just maybe, there's something fundamental we're missing. Like maybe there are new particles out there or even new forces that we haven't discovered yet.
New particles, new forces. That would be huge.
It would completely change our understanding of the universe. And who knows what kind of technological advancements it could lead to.
Yeah, that's what I love about this stuff. We're talking about these tiny particles, but the implications are massive.
It's like Schneepat says, studying leptons isn't just about the particles themselves, it's about unlocking the secrets of the universe.
It's about pushing the boundaries of what we know and what we thought was possible.
And who knows what we'll find along the way.
Well, here we are, the final part of our lepton deep dive. It's been quite a journey, huh?
It has. I mean, who knew these tiny particles could be so fascinating? Schneepat was right. They really are key to understanding, well, so much about quantum technology.
Absolutely. We've talked about the challenges, the possibilities, the mysteries. But now, I'm kind of curious, where do we go from here? What's next for lepton research? What do you see happening, say, in the next decade or two?
Ooh, that's a fun question. Well, for quantum computing, I think we're going to see some major leaps forward with those electron-based qubits. More powerful, more stable quantum computers, that's definitely on the horizon. But you know what's really exciting?
What's that?
The possibility of using other leptons as qubits, muons, maybe even taphas, who knows? That's uncharted territory.
Whoa, hold on. So we could go beyond electron-based quantum computers.
Yeah.
So like muon-powered computers, what would that even look like?
Hard to say, but that's what makes it so exciting. Each lepton has its own quirks, its own strengths. So who knows what kind of computational power we could unlock.
It's like a whole new world of quantum possibilities.
Exactly. And speaking of possibilities, let's not forget those neutrinos. Schneepat, he's pretty bullish on them for communication, right?
Yeah, he seems to think neutrino-based communication is just around the corner. Do you agree?
It's definitely possible. It's a tough challenge, for sure. but the rewards are huge. Imagine submarines talking to each other underwater, no problem. Spacecraft sending data back from, I don't know, Jupiter instantly. No more waiting for signals to travel across the solar system.
That would be incredible. But let's be real. What are the biggest hurdles we got to clear to get there?
Detection, always detection. Neutrinos are just so darn hard to catch. They interact so weakly with matter, it's like trying to grab a shadow. We need much, much better detectors, ones that can pick up even the faintest whispers from these neutrinos.
Right, like first you have to figure out how to even see the neutrinos
Yeah.
before you can build a communication system around them. That's a big ask. And what about those muon anomalies? Schneepat seemed to think those could point to some new physics. Do you think we'll get answers to that puzzle anytime soon?
I think so. I'm optimistic. With all these new particle accelerators coming online, we'll be able to study muons and other leptons in ways we never could before. More detail, more precision. I think we'll definitely crack that mystery. And who knows, maybe it'll even lead to the discovery of new particles, new forces, new physics beyond what we even know exists right now.
So it's not just about understanding leptons, it's about understanding the whole universe, really.
Exactly. It's all connected.
Well, this has been amazing. A real deep dive in every sense of the word. I'm walking away with a whole new appreciation for these tiny particles.
Me too. And I think that's what Schneepat was hoping for, to get people excited about the world of leptons and all the mysteries they hold.
Definitely. So before we sign off, I want to leave our listeners with a little something to ponder. The study of leptons is just getting started, really. So what do you think the biggest breakthrough will be? A super powerful quantum computer running on muons, a neutrino-powered internet. Or maybe the discovery of something totally unexpected, something that changes everything we thought we knew about physics. Who knows? But that's the beauty of science. The journey of discovery is just beginning.
That's it. Keep those minds curious, folks. And never underestimate the power of a tiny particle to change the world.
Couldn't have said it better myself. Thanks for joining us on this incredible journey into the subatomic world. And until next time, keep exploring, keep asking questions, and never stop learning.